also from Jan Hoffmann's group, and it's Di Wang who will present the algebraic framework now this time for static analysis of probabilistic programs.
So good afternoon, everyone. And it seems that I'm the last thing between you and the social hour. So let's do that. And I'm very glad to stand here to present my current work on static analysis for probabilistic programs. And it's a joint work with Professor Jan Hoffmann from Carnegie Mellon and also Tom Rett from Wisconsin. So from the previous talk, I think you already know what is probabilistic programming. So it's just like standard programs with these two new constructs. One is that you can draw random data from distribution, and the other one is that you can condition your control flow at random. To illustrate that, I'll use this program on this slide as the running example of my talk. I used the C-like syntax, and it's with these two new constructs with highlighted by yellow. The first one, the B1, is drawn from a Bernoulli distribution, which just means a coin flip. Bernoulli 0.7 means that the coin flip is a biased one, which that it returns 1 with probability 0.7. And the other conditional here just is an example of a random conditional statement. So for such kind of probabilistic programs, it's very different in semantics, because for a given input, even if there's no non-determinism, you can have different outputs. So we usually model the semantics of a probabilistic program as a distribution over all possible executions. So one application of probabilistic programming is to model Bayesian networks. Bayesian networks are widely used in probabilistic reasoning, and it has many applications in, for example, healthcare. And here is an example of a Bayesian network for cancer. So it's Bayesian networks are used to specify conditional distributions among variables. And here you can see that we can model the probability that one has cancer based on the pollution level and whether the person is a smoker. A typical query we want to know about this network is that we want to query about the posterior distribution specified by the network, such as if I know the X-ray result is positive and the person is a smoker, what's the probability that he has cancer? So one way to think about the problem is that we can treat Bayesian networks as probabilistic programs. And here I use a simpler network to illustrate the transformation. For here, it just stands for the simple random conditional statement. And to make the example more interesting, we can add a loop structure. So it just and the corresponding network will be like this. And this program is exactly what I put on one former slide. So for such program, we want to also do some queries like, what is the probability that B1 and B2 are both false when the program terminates? Or even for the same program, we can ask a slightly different question. What's the expected termination time? And the metric here is use the tick function. We want to count for the expected ticks when the program terminates. So for such programs, there's a common technique, and I call them sampling-based techniques to do such queries. This technique basically simulate the program and do a frequency count, and then you can approximate the answer. And such techniques are very flexible and universal, but some of them are potentially unsound and inefficient because they are using this kind of pseudo-random number generator, and because you are just simulate the whole distribution, you only get a finite number of samples. Then what about static analysis? So people also try to use static analysis method to reason about probabilistic programs, and there have been a lot of work on that. And COUSOT proposed probabilistic abstract interpretation framework to do such kind of reasoning, and this framework is very sound, flexible, and also universal. But their concrete semantics in that framework resolve probabilities prior to non-determinism. To illustrate that, I will show an example in a following slide. But the point I want to make here is that sometimes it's also desirable to resolve non-determinism prior to probabilities. So here, I use a star to denote a non-deterministic choice, and this kind of non-determinism can come from different sources, such as you are doing an abstraction over a program, and also this kind of non-determinism can come from external environment. And here, for COUSOT semantics, because the probabilities are resolved prior to non-determinism, so we need to enumerate all possible combination of these random conditionals. So for this, so first we can choose both the then clause of the two statements, and this will have probability 1/4. Similarly, we can do this, and we can also choose the then clause of the first random state conditional, and the else branch of the second conditional. And at last, we can do this one. And then if we collect all such resolutions, we'll conclude that their semantics will yield that the expected value of t here stands for the number of ticks, will be in a set 1.25, 1.5, and 1.75. But for the program, we observe that the two branch of the outside if statement is identical. So it will sometimes be desirable to say that, okay, if we look at either one branch, the expected time is 1.5. So for the whole program, it should be 1.5. And our semantics can yield this result. And so based on this kind of new resolution of non-determinism, we develop a denotational semantics which can give you the answer that the expected time of the example in the former slide is 1.5. Based on that, we develop an algebraic framework for interprocedural data flow analysis or first-order probabilistic programs with a list of features like recursion, unstructured control flow, divergence, non-determinism, and some common features like sampling and conditioning. We hope that our framework can help people design a new analysis and prove its correctness, and at last implement a prototype more easily. We also try to evaluate our framework. We reformulate two existing analyses, such as the Bayesian inference, as I just mentioned in the example, as well as the Markov decision problem. We also use that to develop a new analysis domain called expectation-invariant analysis. So for the program I mentioned before, our framework can be instantiated to answer such queries, like we can prove that the probability that B1 and B2 are both false at the end of the program is 0.15. Also, we can answer the question that the expected termination ticks is 5/6. So now, here is like I just motivate why we want to do a new denotational semantics and why we want to develop such a analysis framework. Then I'd like to say a little bit about what is our algebraic framework like. So basically, it's based on a principle that's to think algebraically. it's like any static analysis method performs reasoning in some space of program properties, as well as you have some property operations. For example, your programming language may have a list of statements like skip, like the assign statement, and so on. And you use a semantic function to map these constructs into a universe of program properties. And then you can define control flow actions on these properties, like you want to compose to program, or you want to do a conditional choice of the two programs, and so on. So here, we can think this as a method to assign concrete semantics. But if we use another semantic function, we can think this as an abstract semantic function which maps your programming language into an abstract domain where you want to perform your static analysis. So by doing this way, if we want to prove our analysis is sound, you only need to show that your abstract mapping function is a sound approximation of the concrete one, as well as you need to prove that your operations soundly approximate the concrete ones. Then, to make it algebraic, we categorize these properties and operations by a bunch of algebraic laws. To give a sense, we have this definition in the paper, and M is just a universe of the program properties, and the four operations in the middle, it corresponds to all the control flow actions we want, such as composing to program. And here is some bottom and identity element. So besides this, we also have a bunch of algebraic laws to categorize the semantics, such as we want some sort of commutativity and as well as associativities. Now, I just introduced our algebraic framework. Then I want to talk about how to use this kind of semantic algebra to analyze a probabilistic program. Firstly, we need to come up with a proper representation of the programs. So if we look back into traditional static analysis, you'll find that control flow graphs are very commonly used representation for programs because they are good means to separate control flow and data flow. And for traditional static analysis, we reason about the path on the directed graph because to some sense, these paths are independent, so we only need to collect all the paths and to reason about their properties. But in the probabilistic setting, things become different because we want to reason about distributions over paths. So different paths can have different probabilities, and all these paths, along with these probabilities, form a distribution. So in this sense, paths are no longer independent. Here, this can be treated as a traditional path in a traditional program. But in a probabilistic program, a path could be a tree-like structure, and this branching point becomes you need to treat them as a whole entity because they can carry different probabilities. And for here, even the standard conditionals here, we want to treat them as a probabilistic branch because the variables in the program can have random values. And because we want to resolve non-determinism prior to probabilities. So in this formalization, non-determinism is modeled by collections of such distributions to achieve our goal. So if we zoom in to the path, you'll find that for a branching edge, it's desirable to treat them as a single edge, where has one single source node but multiple destination node. So based on this observation, we introduce this kind of control flow hypergraphs where each edge can have multiple destinations. And for the example, for a run example, the control flow hypergraph is like this, and the node on the graph stands for program locations, and the program actions are labeled on the edge. So on this kind of hypergraphs, we want to assign meanings to each node by the summary of all computation that can continue from that node. So for the Boolean program here, what we want to say about the yellow node, what's the meaning of that? We want to say that if we start with the evaluation of B1 and B2, such as B1 is true or B2 is false, what will we reach? What will we reach at the end of the program? What's the distribution of the final valuations of the variables? So to illustrate that, the semantics of this node is like if you have initial values of B1 and B2, then you'll have different final distribution depends on their concrete values. Now we can use the semantic algebra to transform the hypergraph into an equation system which carry the meaning of the program. For this stage, because it's a normal statement, we do a sequencing operation, which means you want to compose to program. And for the conditional and the probabilistic choice, you want to reason about the meaning of the source node by the meaning of the destination nodes. Then we can use this semantic algebra to interpret these operations. Then you get an equations of the meanings of each control flow node. So the point here is that if we use concrete semantics to interpret this operation, you obtain a solution as a concrete semantics. But if you use the abstract semantics to interpret these operations, then the system represents the analysis problem you want to solve. So I just introduce the algebra framework and how to use the semantic algebra to perform analysis on probabilistic programs. And last, I want to introduce say something about our evaluation. So we instantiate our framework to existing analysis, one spatial inference, which I used as a round example, and the other one is Markov decision problem, because and we reformulate their abstract domain in our framework. So after the instantiations, this analysis have the full ability of our framework for free. So specifically, we obtain interprocedural analysis for the two problem. At the meantime, we also develop a new abstract domain to do expectation-invariant analysis. And these invariants are just inequalities between initial values of variables and their expected final values. For Bayesian inference and Markov decision problem, we obtain a bunch of benchmark from a probabilistic model checker, and we can show that we can achieve the same precision. And also the time, the analysis time is reasonable because we just collect, because these benchmarks are relatively small. And for the expectation invariant analysis, we also collect benchmark programs from the literature, and also we craft some programs to illustrate the new abilities of our analysis, such as interprocedural analysis. And here we can show that we can derive non-trivial expectation invariants, like such as the expected value of x plus y is is increased by 4 from their initial values. For the full table, you can refer to the paper. So to summarize, we present a framework, and we hope it can help you design static analysis for probabilistic programs more easily, and you can also prove its correctness in the framework as well as any implementation. We introduce the hypergraph semantics to resolve non-determinism prior to probabilities, which is desirable in some cases. We also show that we can instantiate this framework to different domains to obtain meaningful results. So currently, our framework only supports first-order programs. There's no function pointers, and as well as compared to COUSOT's abstract interpretation, our formulation is not Gauss connection, so you don't have the full power of abstract interpretation. So in the future, we hope to extend our format to support more features and want to develop more useful analysis based on the framework. And thank you.
Hey, that's interesting work. So I had a question on the. So I guess this is for discrete distributions only, or discrete distributions, or this focuses on discrete distributions.
Yeah, for the 3 instantiations, these are discrete distributions.
Okay, and then for like I think Stephen McGill and like Mike Hicks had this work like 2011 or so on like abstract interpretation for. So how does this relate? Like they were using numerical domains to abstract. So an abstract element was just a set of probability distributions, like the concretization. So how does this work relate to this work?
So you're asking for the previous abstract interpretation based.
Yeah, that was like I think in 2011 or so. On,
yeah. Oh, okay. I see. It's like I look into former abstract interpretation based techniques for probabilistic programs, and their concrete semantics seems to resolve probability prior to non-determinism. So in some cases, we want to resolve the non-determinism in a different order. So then in this case, our semantics, our concrete semantics are substantially different. So they develop different tools. But if you prefer the probability prior to non-determinism semantics, you can use COUSOT and related abstract interpretation frameworks, and then you can both have the full power of the AI framework, as well as you can lift traditional static analysis to the probabilistic setting for free. But if you prefer our semantics, so it's another story.
Okay, good, thanks.
Hi, thanks for the talk. So my question is, why do you use hypergraph representation? Why not abstract syntax tree representation?
So the hypergraph here is just a convenient representation of the notion that we want to treat all the paths in as a whole. And how to say that? I'm sorry. It's like here we want to use this representation to express that we want to treat this kind of this branching edge as a whole entity. So you can actually you can just use Markov decision process with different kinds of nodes to express the same meaning, but it's a more convenient way.
I see. I mean, do you have programs which have unstructured control flow? If not, then an abstract syntax tree might give you a more structured representation, and a lot of problems might be simpler. That's my intuition.
Yeah, in our we add some programs to our branch bar, which we can use break and continuous in a while loop,
I
so
see.
we can obtain the correct result.
Okay, thank you.
Thanks.
Any more questions? Okay, if there are no more questions, let's thank Dee again.
Thanks.